Hello students, in this lecture we will see next topic which is cosets. So let's see the theorem. So the statement, let H be subgroup of G, let H be subgroup of G, and let the relation tilde L be defined on G by defined on G by A equivalent to B, A equal to B, this is L, A equivalent to B if and only if A inverse B belongs to H, and let if tilde R be defined by A equivalent to B R, so I will write it as A equivalent to B R means tilde R relation, so A equivalent to B if and only if A into B inverse belongs to H, then to prove that tilde L and tilde R both equivalence relation on G are both equivalence relations on G. So here we have given two relations. So here tilde L, so tilde L means inverse which is on left hand side. So here tilde L is inverse on left hand side, A inverse B belongs to H, and tilde R, so inverse is on right hand side, so A B inverse also belongs to H. Then to show tilde L and tilde R are equivalence relation. So what is meant by equivalence relation? So when we say that tilde is an equivalence relation, so we have the definition: tilde is equivalence relation if and only if equivalence relation if first condition tilde is reflexive, second is tilde is symmetric, and third condition tilde must be transitive. So if these three conditions satisfy, then we say that tilde is equivalence relation. So what is meant by reflexive relation? So for reflexive relation we want one element. So in that relation I will put B is equal to A, then A equivalence to A, then we see that the relation is reflexive. Now for symmetric relation, now we have the condition if A equivalence to B, then it must satisfy B equivalence to A, then we say that this is the symmetric relation. Now transitive relation, now for transitive relation we want three elements, and we have the condition if A is equivalence to B and B equivalence to C, then show that A is equivalence to C. If these three conditions satisfy, then tilde is equivalence relation. Let us prove this. Tilde L is equivalence relation. So we will prove one of them and another will be remaining for you. So here let's see the proof. Now here we have given H is subgroup of G. Now we have to show that tilde L is an equivalence relation. Now to show tilde L is an equivalence relation. So here what we have given, H is subgroup of G. H is subgroup of G means what? H itself forms group, means H itself satisfy all the properties of group, right? Now to show it is equivalence relation means first to check tilde is reflexive. So first reflexive. So what is the definition for reflexive relation? So here if A equivalence to A, then we say that this is an equivalence relation. So here in this expression, so here A equivalence to B, so I will replace B by A. I will replace B by A in this expansion. So what will we get? So A inverse A. So A inverse A will be identity, because A inverse is the inverse element of A. So A inverse into A, which is equal to identity, and we know that H is subgroup, means what? Identity element will belongs to H. So here I will write, let A belongs to G, then what will we get? So A belongs to G, then we know that A inverse also belongs to G, and what will we get? A inverse into A will be identity. Then we know that GB group and HB subgroup of G, then A inverse also belongs to G, then A inverse also belongs to G, and G forms group, means what? Closeness property satisfied, means what? A inverse into A, which is identity, also belongs to H. So A inverse A is identity, belongs to H, means what? So by using this relation, so A equivalent to B, which is A inverse B, and here A inverse A means what? We will write A equivalent to A. So this is left hand side. So A inverse A is equal to identity, means what? A equivalent to A. So since H is subgroup of G and identity will belong to H, thus what we get? Thus A equivalent to A. Now to show second condition, symmetric. So this is reflexive, symmetric. Suppose A equivalent to B, means we have the condition this, and to show B equivalent to A, then so by using A equivalent to B, what is the condition? A equivalent to B, which is A inverse B belongs to H, right? So A inverse B belongs to H, then we know that H is subgroup, then inverse of this element also belongs to H, right? So since H is subgroup of G, then inverse of element A inverse B also in H, that is what we say, A inverse B, or I will write it as A inverse B inverse also belongs to H. So to find out inverse of A inverse B, so what is inverse of A inverse B? Because inverse of A inverse B will be, so this can be written as B inverse A, which is also belongs to H, because here A inverse B into B inverse A is equal to, so what will we get here? A inverse B into B inverse A, so B into B inverse will get cancelled, so finally we will get A inverse into A, and A inverse into A, which is identity. So product of these two elements is equal to identity, then we say that inverse of this element will be B inverse A, right? Because we know that the definition A into B is equal to identity, then we say that inverse of B is A, means B inverse is equal to A, right? So or I will write, or we say that A inverse is equal to B, right? So here what we get? Product of these two elements is equal to identity, means what? A inverse B whose inverse is equal to B inverse A. So here A inverse B inverse, which belongs to H, and this is nothing but B inverse A, right? So using this, so B inverse A also belongs to H, and by using this condition, so here if we have A equal to B, and if and only if A inverse B belongs to H, here B inverse A, so from that then what we get? B equivalent to A, so this is L. So this is left hand side. So symmetric relation satisfies. Now third one is transitive relation. This is symmetric. Now transitive. For transitive relation, we know that we want three elements. Now suppose we have A equivalent to B and B equivalent to C. C. Then A equal to B means what? A inverse B belongs to H. Then A inverse B belongs to H, and B equivalence to C means what? B inverse C belongs to H. B inverse C also belongs to H, and H forms subgroup means what? Product of these two elements also belongs to H means what? This is the closeness property. Then what will we say? Then A inverse B into B inverse C, which is equal to, so by using associativity, A inverse B into B inverse into C, which is equal to A inverse C belongs to H, because product H is subgroup, since H is subgroup of G, therefore H itself forms group, so product of these two elements also belongs to H. So B into B inverse, which is identity, so remaining elements A inverse C, which also belongs to H. So from that condition, what we say, if A inverse B belongs to H, then we say that A inverse C, right? So we say that, hence, so A is equivalent to C. So A is equivalent to C means what? Here tilde L is reflexive, symmetric and transitive means what? Tilde L is equivalence relation. Here therefore tilde L is reflexive, symmetric and transitive. Reflexive, symmetric and transitive. Therefore tilde L is equivalence relation. Hence the proof. Now in similar manner you can show that tilde R, so tilde R can be defined by A B inverse belongs to H is an equivalence relation. Now let's see the definition. Cosets. So cosets. So define this. Let H be subgroup of G, then subset defined by AH. AH is equal to A into H, such that H belongs to capital H of G is the left coset of H, is the left coset of H containing A. So if I multiply H by A on left hand side, then this is the left coset of H containing A. Now if I multiply A on right hand side, then which is the right coset of H containing A. So while the subset HA, which is defined by, so this is HA, so H is on right hand side, so it can be written H into A such that H belongs to set H is the right coset of H, is the right coset of H containing A, This is the coset definition of coset. So here this is the in general definition AH. So if operation is multiplication, then we will write A into H, which can be written as AH such that H belongs to H. If operation is additive, here operation is multiplication. So if operation is additive, then left coset will be written as A plus H, which is here A plus H, which is equal to A plus H such that H belongs to H. Whenever this happen, if operation is additive, and if operation is multiplicative, then multiply H on left hand side, and operation is additive, then add A on left hand side. So this is additive operation and this is multiplicative operation. So in similarly HA, which is the right coset of h containing a. So if operation is multiplicative, then this can be written as h into a, and if operation is additive, then it can be written as h plus a, which is the element h plus a, such that h belongs to subgroup h belongs to capital H, where h is subgroup of G, right? So this is in general definition. If you have given group is additive, then we will write it as h plus a or a plus h. So a plus h is the left coset of h containing a, and h plus a is the right coset of h containing a. So this is additive additive notation, and this is multiplicative notation, right? Let's see the example. Exhibit the left cosets and right cosets of the subgroup 3z of subgroup 3z of z of subgroup 3z of z. So exhibit the left cosets and right cosets of subgroup 3z, means to find out left coset and right cosets of 3z. So here we know that coset forms partitions. So what is meant by partition? So if it forms partition, suppose P1 P2 of z, then P1 union P2 will be whole set z, and their intersection P1 intersection P2 will be phi. So here means what? Which forms partition means we have to find out subset whose union will be set of integer or whole set, and whose intersection will be empty. So here our notation is, we know that z is operation under addition, so our notation is addition. So here our notation is addition, our notation is additive. Now so the left coset of 3z, to find out left coset and right coset of 3z. Now so left coset of 3z containing a and containing a is, so what is the left coset of 3z containing a? So which is a plus 3z, and right coset of 3z containing a will be 3z plus a. Now here we will start from a is equal to 0. Then what will we get? Now taking a is equal to 0, then we get, what will we get? A is equal to 0, then we will get directly 3z. So 3z has element of the form here minus 9, minus 6, minus 3, 0, 3, 6, 9 and so on. So which is 3z. Now it is itself one of its left cosets. So it is itself one of its left cosets. So here first coset. Now I will put here, this is first partition. Now next I will put a is equal to 1. Then so which is coset containing 0. Now to find another left coset, we select an element of z not in 3z. So to find another left coset, we select an element of z, not in 3z. Means here we have z has the element of the type. So what is z? Z is set of integer, and set of integer has the element of the type. Suppose I will write here minus 3, minus 2, minus 1, 0, 1, 2, 3 and so on. I will select the number a which is from z but which is not in 3z. So here we have 0 here, right? Now I will what is the number which is next to 0, which is 1. 1 is not belongs to 3z but which belongs to z. So here I will put a is equal to 1. So put a is equal to 1 and find left coset containing 1, and to find left coset containing 1 which is 1 plus 3z. So 1 plus 3z is equal to, so add this 3z with 1. So what will we get? So if I add 1, then 1 minus 9 which is minus 8. So 1 minus 6 which is minus 5, 1 minus 3 which is minus 2, 0 plus 1 which is 1, 1 plus 3 4, 6 plus 1 7, 9 plus 1 10, and so on, which is the coset containing 1. So these two left cosets. So here first coset is 3z and second coset is 1 plus 3z. So this is does not exhaust z, means what? If I take union of these two, which is not equal to z, because here this has element 1 minus 2. So here 1 0 1. So 2 is not there in both the partitions. So here 3z and 1 plus 3z, there is no 2. So 2 is neither in 3z nor in 1 plus 3z, means we will take another partition, or we have to find another cosets which is containing 2. So now these two left cosets 3z and 1 plus 3z does not exhaust z, because 2 is not there in both the cosets, because 2 is neither of them, So next to find out coset containing 2. Now to find coset containing 2. Now to find coset containing 2. So coset containing 2 will be 2 plus 3z. So which is equal to, so I add 2 with 3z, then what will we get? Here 2 minus 7 minus 9 which is minus 7, next 2 minus 6 which is minus 4, 2 minus 3 which is minus 1. So 2 plus 0 2, 2 plus 3 5, 2 plus 6 8, and so on. So here if I take union of these three sets, so we will get z, because here if I we have the element here 0 1 2 3 4 5 6 7 8, means all element covered in these three cosets which is equal to z, means what? So it is clear that these three left cosets we have found to exhaust z, means what? Union of these three cosets will get z, hence so they constitute the partition of z into left coset of 3z. Since z is abelian, then left coset of a plus 3z and the right coset 3z plus a are same, because here 2 plus 3z and 3 plus, so I will write here 2 plus 3z is same as 3z plus 2. So left coset and right coset will be same whenever G is abelian group, right? So here we will write next note, but here how many cosets are there? Total 3z, 1 plus 3z and 2 plus 3z. Total there are 3 cosets of 3z in z. Therefore 3z, 1 plus 3z and 2 plus 3z are 3 left cosets of 3z of z, are 3 left cosets of 3z of z. So let's see the note. So if group is abelian, if G is abelian, then left coset of H, then left coset of H containing A is same as right coset of H containing A, right coset containing A whenever J is abelian. So we have seen that 2 plus 3Z which is same as 3Z plus 2, because 3Z has element 0, 0 plus minus 3 plus minus 6 plus minus 9 and so on. If I add 2, then we will get same element. So we know that 3Z is abelian or Z is abelian, then left coset and right coset will be same. Now let's see the another example. The group Z6 is abelian. The group Z6 is abelian. Find the partition of Z6. Find partition of Z6 into cosets of subgroup H. So H has element 0, 3. So let's see the solution. So first write down Z6 has element 0, 1, 2, 3, 4, 5. Now to find out partitions of H containing these elements. So let us find out. So first let here H is equal to 0, 3. Now first find out partition of H containing 0. So then left coset containing A, then left coset containing A. So here operation Z6 is additive, so I will write here A plus H. So A is A plus H, right? Therefore taking A is equal to 0, so because here first element 0, now taking A is equal to 0, then left coset of 0, so left coset of H containing 0, so 0 plus H will be H and H is equal to 0, 3. For A is equal to next element 1, so A is equal to 1, then 1 plus H will be 1 plus H means what? 1 plus set 0, 3. So here add 1 to each element, so what will we get? Which is 1 and 4. Next A is equal to 2, next element, so what will we get? A is equal to 2, then 2 plus H which is equal to 2 plus H is 0, 3. So adding this with 2, so 2 plus 0, 2, 2 plus 3 which is 5. And next here we have H, 1 plus H, 2 plus H. Now if I take 3 plus H, then so if I take another set which is 3 plus H, so here H is equal to 0, 3 is itself one of its cosets, is itself one of its left cosets, right? And to find another coset, put A is equal to 1, we will get another coset 1 plus H which is 1, 4. If I put A is equal to 2, then we will get another coset which is 2 plus H has element 2, 5. Now here observe that here total there are 6 different elements. So 0, 1, 2, 3, 4, 5. Exhaust all elements of Z6 means what? H, 1 plus H, 2 plus H forms partition of Z6. Here since what are the elements we get here? Since here first set has element 0, 3, second element has element 1, 4, third coset has element 2, 5. Exhaust all Z6, all of Z6 means union of these 3 sets will be Z6 means what? Which forms the partition, because there is no common element between these two. Suppose I will take, so there is no common element between these 3 and union of all these 3 sets will get Z6 means these 3 sets exhaust of Z6 means union will get Z6 means this forms partitions, right? Hence what we say here, hence first set H 1 plus H and 2 plus H are three left cosets, and also here we know that G is abelian, then we know that left coset and right coset are same, therefore also left coset and right coset are same, cosets are same, since why G is abelian. So we will get total three different cosets. So here what we say, left coset and right cosets are also same because G is abelian group. Let's see another one example. So in previous two example the operation is additive. Now let's see the operation is multiplicative. Let H be subgroup of S3 and generator phi. So we know that generator phi has elements identity and phi of S3. Find the partition of S3. Find partitions of S3 into left coset of H into left cosets of H and partition into right cosets of H and partitions of right cosets of H, right cosets of H. So let's see the solution. Means we have to find partitions of left cosets of H and partitions of right cosets of H. So here we know that S3 is always, we say that S3 is non-abelian, and we have given H is subgroup which is S3, which is the generator phi, and generator phi has element identity and phi. Now we know that in S3 has element identity psi square, next phi psi such that phi square is equal to psi cube is equal to identity and phi psi is equal to psi square phi. So this is the property of S3, element of S3. Now here generator phi has element identity and phi. So here this is the multiplicative group, means here operation will be multiplicative. Now here this is the H. Now so find out the left cosets of H containing first key. So H is equal to identity and phi, it is itself one coset. Now next coset, so here if I multiply by identity, then we will get as it is. Now next element we will multiply by psi, then what will we get? Psi into H. So multiply on both sides, so psi into H, so multiply psi, then what will you get? Psi into identity and here psi into phi. So after solving this we will get, so psi is on left hand side, so psi into identity will be psi and psi into phi. So these are two elements. Next I will multiply psi square, so psi square into H which is equal to, so multiply on this, so psi square into identity and next psi square into phi which is equal to psi square into identity which is psi square and psi square phi. So psi square phi has value phi psi, so which is phi psi. So here we get all elements, so identity psi square, phi psi phi psi. So all elements we get in three sets. So here what we say, therefore H psi square H are three left cosets of H. So here three left cosets. Now So this form the partition because there is no common element between this between any two, and union of these three sets will get S3. So this forms the partition. So these are three left cosets of H. Now to find out right cosets, now the right partitions into right coset is the partitions into right cosets of H is, so here H is identity and phi. So to find out right coset means I will multiply this element on right hand side. So first if I multiply H into identity, then we will get as it is. Now next I will multiply H into psi. So psi is on right hand side. So identity into psi, and here phi into psi. So which is equal to identity into psi, which is psi, and this is phi psi. Next I will multiply next element psi square on right hand side. So H into psi square, which is equal to identity into psi square and phi into psi square, right? So multiply on that side. So which is equal to, so identity into psi square, which is psi square, and we know that phi into psi square, which can be written as phi into psi, and this is psi. So we know that phi into psi has value psi square phi, and this psi as it is. So again we know that phi into psi has value psi square phi. So this psi square and this value has psi square into phi. So this is psi raised to 4. So psi raised to 4, we know that psi cube is identity. So we will get only psi phi. So this is psi phi, right? And so here we get identity psi square, next phi psi and psi phi. So this again forms the partition, means union of these three partitions, means union of these three cosets will get whole S3. So here these are the partitions. So the partition into left coset of H is, so which is here what we say psi H and H psi is not same, because here psi phi and phi psi are different elements. So both are different elements. So here we see that left cosets of H and right cosets may not be same, because here psi H is not same as H psi, because here in these two sets, so psi is same, but here is second element, this is the psi phi and this is phi psi. Both are not equal because they are they are different element in S3. So the set, we say that the partitions or left coset and right cosets are not same. Therefore partition into left coset of H is different from the partition into right coset, because psi H is not equal to H psi. So psi H is not equal to H psi. And so what are the left cosets of H containing psi square, which is psi H psi square H are 3 left cosets, and H psi square are 3 right cosets. Therefore H psi square H are 3 left cosets of H, and H psi square are 3 right cosets of H, and which forms the partition, means their union will be whole set S3. Now let's see the note. If G is non-abelian, then left cosets and right cosets may not be equal. Then left cosets and right cosets may not be equal. Here we have seen in previous example that psi h is not same as h into psi. So both are unequal because h has element identity and phi, right? So phi psi not same as psi phi. That's why if group is non-abelian, then left coset and right coset are different. Okay, we will stop here. Now in next lecture we will see Lagrange's theorem. Thank you.